Okay, let's get started. So I'm going to continue the part of the lecture I couldn't finish yesterday. Then we'll switch to threads. I will also at the end of today's class talk a little bit about the first lab, which is out. It's time to start doing some real work in this class. Right, so it's going to be on system calls. So I'll talk about that towards the end of the class. So let me just wrap up yesterday's slides that have overflowed today. So if you remember, you lost more half of the class. There must be something new today. That's what I'm guessing. So if you remember from yesterday, we basically started talking about CPU scheduling processes, and talked about preemptive, non-preemptive schedulers, and I have introduced so far 3 different scheduling algorithms. Okay? First come, first serve. What are they doing? Round robin.
Shortest job first.
SJF, shortest job first, SRTF. Okay? So we said SRTF, good policy in terms of optimizing wait time. In fact, it is optimal. There's no policy that will do any better if optimizing wait time is your criteria. But it has a fundamental flaw. It requires the job lengths to be known ahead of time, which is not a practical assumption for any real kernel. Okay? In some specialized schemes that may be okay, but not in general. So now, but we like the approach because it does some interesting things for us. So I said it favors I/O bound jobs over CPU bound jobs. We said we like that because it allows more overlap of I/O devices and computation. It reduces wait times by letting these I/O jobs get CPU time as soon as they become ready to run, and then they go back to doing I/O. So all of those are nice properties, but it requires you to know the job lengths, which is not practical. So we are going to see how to derive a more practical variant that will try to approximate what SJF does, but eliminate its disadvantages. And want to retain its advantages and eliminate the disadvantages. Okay, this technique is scheduling algorithm is referred to as a multi-level feedback queue, MLFQ. Okay? This is a reasonable approximation of what actually many Unix-like CPU schedulers actually do in practice. Okay? They will employ some variant of this, not necessarily just this, but some variant of this. Okay? Back in the days when uniprocessors were developed, there are some issues with this when you go to multi-core and multiprocessors, which I will not go into. Okay? So here is the approach. Okay? So it basically, what you have is not one, but n ready queues. Okay? Each has a different priority level, and within each queue you are going to do round robin. So this is really a generalization of the round robin approach, where instead of one round robin queue, we will have n round robin queues, and these queues will have different priorities associated with it. This is this top queue. So these are 4 queues here. In this case, you can have n. Here n equals 4. This one has priority 1, priority 2, priority 3, priority 4. Lower priorities are better in this case. Okay? This is the highest priority queue, the next highest, and so on. Okay? So in this case, you will see that there are some number of processes that are waiting to be scheduled. Okay? So whenever the scheduler runs, it will start looking for the highest priority queue that is non-empty, and pick a job from that queue, a process from that queue, and schedule it for execution. Okay? So in this case, whenever the scheduler runs, it will start with the highest priority queue. This is non-empty, so you pick A and you schedule A for execution. Okay? If A finishes its time slice, it will go back to the end of the queue. It will again start at the top queue. If there is a top queue empty, it's not, so there is something to schedule, then it will pick F. So you will do round robin in this case here. Okay? If this queue is empty for any reason, it will then go to the next highest priority queue and do the same thing at that time. Okay? So you are doing round robin within a level. Okay? But you always start with the highest priority non-empty queue and pick a job from there and do round robin at that level. Next question.
Yeah, so like what it says is like as it gets to like the lower priorities, the round robin slices increase exponentially. So what happens if, like, you have this really long slice, and then you have a new process at higher priorities?
Right, okay. So you are asking about time slices. I didn't even mention this. I haven't explained the whole scheme yet. So we will hold on to that question for just a moment. Let me finish explaining the technique. Then if you still have that question, you'll come. I know what you're asking, but I think once I finish the explanation, it will be clear. Okay? So first part, so that's not what all the scheme does. There are many aspects which I haven't even described here. The first aspect is there are n round robin queues, each with a different priority level. Okay? And this is simple prioritized round robin. You pick the highest priority queue that's non-empty and you do round robin at that. If that queue becomes empty for any reason, go to the next highest. That's the first thing. Okay? Second thing, as was just mentioned, is this notion of time slice. Okay, if you look at it, you will see that each of these queues have a different value of a time slice associated. In particular, as the priority level drops, the length of the time slice, in this case double. Okay, it could increase in any exponential way. In this case, as you go down a priority level, the length of the time slice is going to double. What that also says is that higher priority levels, you get smaller time slices. At lower priority levels, you get longer time slices. Okay? Why that is the case will become clear. For now, just assume that that is the case. Okay? Second aspect is time slices increase as priorities drop, okay, as you go down. Okay? Now, third thing is how are tasks assigned to this queue. Okay? So assume you have a new job that comes in, a new process starts up. Okay? By default, it will always join the highest priority. Okay? So default is whenever a new job process arrives into the system, stick it into the highest priority. Okay? Now, once you start getting scheduled, here is how the scheduling mechanism actually works. So if you get scheduled at any priority level, so now let's say you schedule job A in process A, okay? And then you basically look at what it did. So in this case, it will get scheduled for one time slice. That's the length of the time slice. So you look at whether the job finished its entire time slice or whether it started doing I/O before the time slice expired. Okay? If it finishes its time slice, then you basically drop it one priority level. You don't let it join the end of this queue. You say you go down one priority level and you join the end of that queue. Okay? If any job in this queue, any job in the system actually uses its entire time slice, then it has to drop one priority level. Okay? And vice versa. If you give up your time slice, if you are scheduled for a certain time slice and you give up your time slice by doing I/O before your time slice expires, you will rise in priority. Okay? You will actually go back to doing I/O, but when your I/O is done, you will join the higher priority, one queue that is higher priority than where you were previously. Is this clear? The behavior of how jobs. So if you finish your time slice anytime you're scheduled, you drop. Your actually your priority decreases in the system. If you don't finish your time slice, you start doing I/O, your priority rises. Okay? Now let's ask the question, why are we doing all this? What does it give us? Is the scheme clear before we move on to why? Is there a question? Yes.
If one of these jobs is in a process or when its priority changes, does that affect the time slice of the job next to it?
So you are saying if the job is actually executing and its priority changes, does it impact what the time slice is? Is that the question? So first of all, the priorities will change only at the end of your quantum, not during your quantum. Okay? If your process is executing, its priority is not going to change while it is executing. Okay? At the end of the time slice, you ask a simple question. Did the job finish its time slice or not? If the answer is yes, you decrease its priority, decrement the priority by 1. If the answer is no, it started doing I/O before the time slice expired, you increment its priority. That's as simple as it is. So the question you asked shouldn't occur at all. Because the job is executing, you are not changing its priority while it is executing. Okay, yes, there's another question. So now let's ask the question, what is all this giving us? Why are we changing the priority in this fashion, incrementing and decrementing this?
We're trying to predict what for SRTF, we're trying to predict whether it's I/O bound or CPU bound, so we can concurrently utilize the resources of the machine better.
Okay, so suggestion or insight is we are trying to predict whether jobs are I/O bound or CPU bound, so we can better utilize the resources. So that's true. We are indeed trying to do that, but the question is how is incrementing and decrementing that priority allowing us to predict that? Yes.
You're also getting rid of the I/O jobs as fast as possible so that the CPU-bound jobs can get priority. But if you get a new I/O one, you can push it in.
So you're basically saying you're trying to get rid of the I/O bound jobs. That is also true. Both of these observations are true, but I want to know why incrementing and decrementing those priorities actually got us to those results. Yes.
We're trying to approximate shortest job first without actually knowing the length of the job. So
Yes.
if the job used its whole time slice without leaving to do I/O, then we can assume that that job is a longer job. So we bump it down to a lower priority. If the job doesn't use its whole time slice, it's a shorter job, so we bump it up. On average, the shortest running jobs will tend to bubble up to the highest priority. The longest running jobs will go down, and so we can approximate shortest job first without actually knowing for sure how long the jobs are.
Okay, so that's a very good explanation of how the technique works. And let me rephrase. There's something in the back. Do you have any comment? Yes, so basically, remember, what are we trying to do? We are trying to approximate shortest job first. We don't know the job length. Okay, so somehow you have to try to approximate the behavior without knowledge of the job length. But you have to understand what was shortest job first giving us. It was giving us the property that we try to favor shorter jobs, which tend to be more of the I/O bound jobs over the CPU bound. So somehow we need to figure out which jobs in the system are I/O bound and CPU bound. Okay. Again, when you start a process, you don't label it I/O bound or CPU bound, just as you don't give any job length. Okay. The system doesn't know. It has to determine this as it goes along. So the way you go about doing this, is you just observe the behavior of the job and try to predict what kind of a job it should be. Okay? So you say, did it use its time slice? If the answer is yes, it is trying to execute as it, and while it does that, it used up the time slice. So you say, maybe this is a CPU bound job, I'm going to treat it as such. Okay? For the other hand, it started doing I/O in the middle of its time slice. You make a guess saying, this job is doing I/O at the moment. So it might be an I/O bound job, so I'm going to treat it as such. Okay, these are just guesses. Okay? It is very likely that your guess is going to be right, in which case you are fine. If not, you can correct. The next time if a job uses its CPU or it changes its behavior, you will adjust accordingly. Okay? This is not a sure thing, but it's actually a good rule to try to label the job. Okay? So we are saying if you use up your time slice, you're CPU bound. Okay, and since we want to favor I/O bound or CPU bound jobs, you try to drop CPU bound jobs in priority. So if you use your time slice, you drop it one level. If you do that again, you drop it. So all jobs that are really CPU bounds are actually going to drop, and they will actually end up in the lowest priority queue. Okay? All jobs that are I/O bound will actually rise in priority. Okay? And so every time you are in any level, you keep rising until you hit the highest priority. Okay? So if you actually add these two classes of jobs, you'll see that I/O bound jobs are somewhere at the top, CPU bound jobs are somewhere at the bottom. Since this is a prioritized scheduler, you'll always start at the highest priority, and since I/O bound jobs are sitting there, you're going to schedule them over CPU bound jobs. Okay? So we have automatically figured out by doing this priority modifications on the fly, which ones are I/O bound, which ones are CPU bound. Using a prioritized scheduler, we are also treating, discriminating in the favor of I/O bound jobs or CPU bound jobs. Okay, so any I/O bound job will quickly get to run. And remember, this is why the time slices are also shorter at the top. Because these are I/O bound, there is no reason to give them long time slices. They will probably not even use that short time slice. Okay, they will basically start doing I/O before that. And here you give it longer time slices because you know these will be CPU bound. So let's amortize the context switch over very long time slice. Okay, so your time slice is higher for that very reason. Okay, if you just do short time slice here, you'll just switch between a lot of CPU bound jobs. That's effectively wasted work. Let them run for slightly longer periods. Okay, that's the reason the time slice is also increasing exponentially.
Yeah. So just to clarify, when you're switching between like the top priority and the second priority, you're not exactly waiting for them to be done with their jobs, but you're just waiting for them to go to I/O.
Right. All we are trying to see, as far as the scheduler is concerned, is only looking at this queue. You start here. Is this queue empty or not? If it's empty, you go, is this queue empty or not? You scan these queues until you find a non-empty queue, and you just schedule the job here. Okay, that's the way the technique works. Now, what is the implication of doing that? You are trying to basically get, if the IO bound jobs are at the top, you'll schedule A. If it is indeed an IO bound job, it's very likely it's not going to use its time slice, it's just going to go off doing IO. So then it goes to the wait queue, it's no longer here anyway. Remember, these are only ready queues. For every state you have a queue, so it will go and sit in the wait queue, so it gets removed from this queue, only these two jobs remain. And then you do the same thing for F and G. And if these are all IO bound jobs, you run them quickly, they're all off, gone off doing IO, this queue is empty. And so on and so forth.
So when they come back into the queue, do they recognize that those were the I/O bound jobs in the first place? Or?
Right. So when you come back, based on what you did in your previous quantum, you will basically be treated accordingly. If you're already at the top, you cannot get incremented anymore. You will rejoin that queue. If an D started doing IO, it went off to the wait queue. When it comes back, it will actually join here, one level up, and keep rising. That's how it will work. Any questions? Any more questions? Okay, it should be clear how this technique works. Okay. Now, the one thing we have not addressed, so this is a good approximation of SGF. It is doing what SGF did. Favors short jobs, favors IO bound jobs. Okay. Amortizes the context switch for CPU bound job by giving them longer time slices. So all of the nice properties are still there, except for one, okay, which is that of starvation. So it should be clear that this, we have done nothing about starvation. Remember in SJF I said, if there is a steady stream of short jobs coming into the system, a long job that's ready to run will actually keep waiting, because there is always a short job to run whenever the scheduler runs. Same is true here. There's a steady stream of IO bound jobs that get ready, become ready to run. Okay, they always join at the higher priority queue, then you will only schedule those, you'll never schedule the one. That is unlikely to happen because by definition IO bound jobs spend long time doing IO. So they'll run for a short period and they'll go. So most of them are actually waiting for IO to finish. But if you have so many jobs, if in the case where you have lots and lots of IO bound jobs, that some job always becomes ready to run and joins this queue, then your CPU bound jobs are in trouble. They are going to sit there waiting for the CPU and never get. Because starvation is not dealt with. We'll see how to address that as well. Okay, but this technique that I just described is not going to deal with starvation. Okay, keep that in mind. So this is already mentioned how to adjust priority very quickly. We are going to do this. It's a little bit of work here. 3 jobs, length 30, 20, 10. Okay, these are 3 queues. Okay, job queue 1, queue 2, queue 3. Those are the time slices. Okay, so this is actually a simple case, all CPU bound jobs, no IO. Okay, you can assume more complex examples where some are doing IO, some are doing CPU and so on. So all 3 jobs start here. Okay. Since you're doing so, all you have to do is 3 round robin techniques in prioritized order. So all 3 jobs here, the job with that 30 will run for 1 time slice. Will, since it's CPU bound, it will use up its entire time slice, it will go here. Okay. And it has 29 more execution units remaining. Then the job with length 20 will start running here, run for 1 time slice, will use it up, it will drop here. Job 10 will, job with length 10 will run, okay. Will run for his entire time slice, it will drop. And then you'll repeat the same thing here. Okay, there's no more round nothing, this job queue is empty now. Go to this queue, will run that job with 30 for 2 time units now, because that's the time slice here. Again, it uses its entire time slice, 27 more time units to go, it will drop here. Okay. Same with the other 2. So all 3 of them will land up here and they have still some time to go. Here you will actually do round robin because you can't drop any further until all those jobs finish. Next question.
Are all of these jobs either user jobs or system jobs, or are we talking about both?
So in this case we are using a generic term job or a process. The reason I keep saying job rather than a process, so far we've only talked about processes, so I could have just as well said processes, is you can use the same techniques to schedule threads. Okay? So job actually refers to it's a thread or a process, which is why I use a more generic term job. But coming back to your question, you're asking, are these user processes, system daemons, right? So that's really the question. So in this case, the CPU scheduler is not discriminated between user level jobs, system daemons. It's a process or a thread that needs to be scheduled. Who this thread belongs to, we have not said anything about users. Right? So we are not distinguishing between users, so you don't distinguish between the root user, which is where all the system processes run, and real users. Okay, so it's immaterial from the perspective of CPU schedulers. Yes.
Just one more question. So like, if they're all like CPU bound jobs, can you literally just have like infinite queues? Like it just keeps adding queues as it goes on, or do you just usually have like a finite number of queues?
Okay, so number of queues is deterministic. It's determined by whoever wrote the CPU schedule. The number of queues is not going to change. Okay, so you may have 4, 8, 32, some number of queues based on whatever the CPU scheduler is trying to do. That is not going to depend on the number of jobs. So whenever your system boots up, whatever the CPU scheduler is gets loaded in the kernel, and whatever queues it defines is what you have in the system. It's not going to change dynamically. Okay. Any other question here? Okay, so this is just sort of a worksheet that shows what's happening to the job. So here, so I'll explain what this superscript, subscript are. So these are the job IDs, okay, process IDs, this, the bold number. So this is job 1, job 2, job 3, you could have called it ABC, doesn't matter. Here there's a subscript and a superscript. This is just a way to figure out what has happened to the job so far and what is the current time. Okay? The subscript, the superscript is telling you how much CPU time has already been used up by the job. How much, for how long has it actually executed. So initially this one executes for 1 time units here, so it has received 1 second of CPU time. It runs for the second time, is going to get a time slice of 2, so it's actually computed for 3 seconds and so on, 7 and so on. Okay? That is the superscript. The subscript here is actually current time in the system. So this is what has happened at time t equals 1, t equals 2, t equals 3, 5, 7, 9, 13, 17. Okay, you can come up with any other scheme so long as you can track what is going on. This is the way we recommend. It's a simple approach, so that you can keep track of what's the current time, how much CPU time has each job received, etc. Okay. All right. So you work through this, you will actually find that these are the completion times of the 3 jobs. Okay. This one finishes at 32, 53, and 60. So you will take that's round robin. I should have actually put SJF there just to compare whether are we approximating or not. You can try that yourself to figure that out. Shouldn't be too difficult. Those are the wait time. Okay, wait time is still completion time minus job length minus arrival time. Arrival times are still 0, so we ignore them. So it's just the difference between this column and this column. For MLFQ and these 2 columns for round robin. Clear? So these kinds of questions can become a little more complicated if we say, hey, job 2 is going to do I/O every other second. Okay, so it may do computation for a burst of 3 seconds, then it does 1 second of I/O. So you have to figure where is it, and then you have to take it out, wait for a second, put it back in another queue as you work through this, and it can become a little more complicated. Okay, here we did the easy case, there was no I/O. Here is one I believe that does I/O. Okay, job, the 10-second job does 1 second of I/O every other second. It computes for 1 second, and then it basically is going to do an I/O which will last for a second and will rejoin already. Okay. So every time it does I/O, it's going to rise. Okay, this is the thing to keep in mind. There are only 2 queues just to keep things simple here. So this is what has happened. So a little more complicated jobs 1, 2, 3 will run. 1 and 2 will drop. 3 is going to do I/O. So as soon as it runs for 1 second, it's time to go do I/O. So you go off into the wait queue. At this point, you will run 1 and 1, and then by the time 1 has finished for 2 time slices, this job 3 is come back, but it does I/O for 1 second. So it will run every other time slice. Okay, it will always stay at the top, and when it goes off doing I/O, you come to this to execute one of these 2 other jobs. Then by the time that job finishes, 3 has come back. So I want to work through this, and you'll see that 3 is always here because this is an I/O. It's not really I/O bound, it's half I/O, half compute, but it's doing an I/O so it gets favorable treatment over the other 2 jobs. Okay? So 1 and 2 are always, once they drop, they're always here, 3 remains there. as we would expect for any job that they're running. Okay. So the rest is, I'm not going to go into all the completion time. If you work through it, you'll see those numbers there. Any questions on this? Okay, so there's one last point here, which is fairness. I said we are trying to approximate SJF. You have done a reasonable job so far, except for one problem, which is starvation. Here's a question: how are we going to deal with it? What can we do? If there's a steady stream of IO-bound jobs, what can we do in the system?
Combine it with round robin.
Okay, how do we do that? We can combine it with round robin is the suggestion. So what would we do?
Well, so you put them in, you put in jobs in queue based on how long you think they will take. And then you shift priority on how long they will take.
Okay. So if I understand what you're saying, you're basically saying that you will play with the priorities to deal with starvation. Okay? So that's indeed what you can do. So if you, very simple thing is you say CPU bound jobs in this case will drop. Okay? They'll stay at the bottom. Okay? The IO bound jobs are at the top. And then you can have a timer associated with each job to say how long has it been since it, if it's in the ready queue, how long has it been waiting since the last time it got scheduled. Okay? If the timer, let's say the timer is 5 seconds. If the timer goes off, you say this job has been sitting here for 5 seconds and it still hasn't gotten scheduled. Okay? It is a CPU bound job, but it's not getting any time on the CPU. Let's say let me try to increase its priority 1 to see if it gets any CPU time by bumping it up. Okay? So essentially what we are going to do is we are going to track our jobs getting starved. They are going to get starved, we will actually bump up the priority. Saying this job is getting starved, maybe we should bump it up so it gets some CPU. So what would happen in this case if there are lots and lots of IO bound jobs which are always in the top queue, CPU bound jobs will sink, they'll sit there for a time, starve for a little bit and they'll rise again. Okay. And then they will actually compete with the CPU bound job, get a little bit of CPU time and they'll drop again, they'll starve for a little bit, they'll rise back. Okay. This is somewhat better than not getting any CPU time at all. It's not ideal. It's a modification saying that you cannot starve for too long. You'll at least get some CPU time if you do this. Okay. Now there are a lot more sophisticated schemes on that allow you to do better use of priority. I just described a simple scheme that dynamically changes the priority also based on whether you're starving or not just based on whether earlier the priority was basically governing or was governed by whether you're CPU bound or IO bound. Here the starvation, if you're starving, your priority can change as well. Yes, your comment.
Oh no, I was just gonna say like if you change the priority and like the CPU bound jobs go back to the top, the quantum is still pretty small at the top.
Yes. So it's an ad hoc solution, that's what it's not a good solution, better than just letting them starve. Okay, you still go back to the top, you still get 1 time slash, you probably should have gotten for something longer because you start and still you only get 1 time slash, but there's some progress in the system. You don't have jobs that get no CPU time at all. Okay, anything that has starvation either means you change the scheduling technique completely, but starvation is a bad property, or you put in a hack which at least tries to mitigate the effect of starvation. This is not taken starvation out. CPU bound jobs are still starving and then they go back and give them like a crumb of CPU. We have taken a little bit behind. Not a good solution.
They also get time slices all the way down after the
Okay. So you get a little bit. It's not an ideal solution, but ad hoc solution. This is what Unix did. I didn't make this up. This is what they did. Saying, oh, there's starvation here, let's try to fix it. Okay. It's somewhat of an ad hoc solution.
Could you do like a circular queue so they always get dumped back on top of the stack at some point? Or
Yeah, you could. I mean, there are as many schemes that you can think of. I'm sure people have tried that. And this is just one solution. There are many others that would try to do something a little smarter than that and so on. That's if you start, but then you get to run, then don't get that time, so get a little longer time. So a whole bunch of things. Okay, but for the purposes of this class, you just need to know how can you make simple modifications to deal with starvation. You can, of course, make more complex modifications. Okay? All right. The last technique, and then we will move on to threads. This one is a completely different kind of scheduler, randomized scheduling, called lottery scheduling. Okay? So, again, this was actually proposed in the research literature. It's not something that many commercial schedulers use today. That's an interesting one to look at. Okay? So all the schedulers we have talked about, they are more deterministic. Their behavior is actually, you can work through examples and figure out what is going to happen and so on. This one is a randomized scheduler. If you have done 311, you should know what a randomized algorithm is. Yeah, randomized algorithm, the behavior is actually not deterministic, it's randomized, it depends on toss of a coin, etc. This will do the same thing. So here is how it works. You are going to give each job some number of lottery tickets. Right? Think of them as real lottery tickets. So you take all the jobs in so whenever the scheduler runs, it will go and say, give me all your lottery tickets. Okay, it will run a lottery. Okay, from all the tickets, it will pick a winning ticket. Okay? The job that holds the winning ticket is the one that is going to get to run next. Is it clear what I just said? Every time the scheduler runs, every job has been assigned some number of lottery tickets. And what that number is, we will see. But let's assume we are given some number. So every time the scheduler runs, you take all the lottery tickets, run a lottery, the job with the winning ticket gets to run next. Okay? Completely randomized. You don't know who is going to win. It depends on what the outcome of the lottery is. Okay? Next time the same thing is going to happen. Okay? Now what does this give us? Why do all this? So first of all, what this allows you to do is by controlling how many lottery tickets are assigned to each process or a job, you can control the fraction of CPU time that's going to get, that job is going to get. The simplest case, let's say you have two jobs, A and B. Each one is given one ticket each. Okay? Each is going to win lottery with probability half, with 50% chance. Okay? So 50% of the time job A is going to win, 50% of the time job B is going to win the lottery. So over some long period of time, you will see job A, because it won the lottery half the time, is going to get half the CPU time, and job B the other half. Okay, so they got equal share of the CPU, 50%, 50%. Okay.
Are the tickets destroyed when they're called, or?
No, the tickets, you have that many tickets every time you just, so even if you win, that ticket doesn't go. You have 6 tickets, you will always have 6 tickets when you lottery. Okay. So if you have job A now has 2 tickets and job B has 1 ticket, okay, job A is going to win the lottery 2/3 of the time on an average. With 66.6% probability, job A is going to win, and job B at 33%, 1/3 of the time. Because the probability you win your lottery ticket is the number of tickets you own or the total number of tickets in the system. Simple probability. So if you have 3 tickets, then and one has 1 and the other one has 2, then job that has 1 ticket wins the lottery 1/3 of the time, with probability 1/3, and the other one is probability 2/3. So over some long period of time, we'll see that now this job gets 33% of the total CPU time, and that job has gotten 66%. This job gets twice as much CPU time as this job, just by changing the number of lottery tickets. Okay? So now you can do interesting things in the system. If you feel like this job requires more CPU time, it needs to compute faster, you can actually give it more lottery tickets. Okay? And the more lottery ticket you give, that's the proportion in which you will actually get CPU time in the system. Okay? This can generalize across any number of jobs I just talked about. So you will basically take all the jobs and you will basically win the lottery with this probability. Okay? It's not deterministic. Okay? Not doesn't mean if you have 1 and 1 ticket, always you will get A, B, A, B. You may get A, B, 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 but over some period of time you will get 1/3, half the slots. Okay? Because it's completely randomized. You don't know, it's memoryless. You don't keep track of A won the lottery, so now this time I'm going to force B to win the lottery. It's randomized. Okay? You can win lottery twice in a row. Probability is very small, but it can happen. Same thing is true here. Okay? So here's a quick example of how this works. So we basically assume, I said short jobs, long jobs, just as a way to think about how this technique works and how to give it appropriate number of lottery tickets. We say in this system, we are going to give short jobs 10 tickets and long jobs 1 ticket. This is just our way of saying that short jobs tend to be IO bound jobs and we want to favor them, so we are going to give them 10 times as many tickets as the long one. If we want to approximate shortest job first, this is what we will do. Okay? Again, remember that when you start, unless you know that this is a IO bound job, only then you can do this. Okay? You as the user need to have some intuition. Otherwise, if you don't know what the kind of job you're running, you can't just say, yeah, I'm going to give it 10. Well, let's assume you do know that this job is very compute bound, that job does lots of I/O, so you could do this and say, I'm going to give it 10 tickets. I meaning you, the user, can in this case decide what the tickets to give. Okay, by default, you might just give it. So in this case, if you have short jobs and long jobs, and you have one short and one long, okay, the short job is going to get 91% of the CPU, and the other one is going to get 9% of the CPU. Okay, that's simply because the short job is going to win the lottery with this probability, and the long job is going to win the lottery with that probability. 10 over 11 is 91%, 1 over 11 is 9%. Okay? Alright, so now we'll assume there are no short jobs, there's only two long jobs in the system. Okay, each of them gets 1 ticket each, so percentage of CPU time each short job gets 0, no short jobs, percentage of CPU time each long job gets is 50. Two long jobs, each has 1 ticket, each of them gets 50% of the CPU. Okay? Situation is reversed. Here there are no long job, 2 short jobs, each gets 10 tickets. Okay? So that's still 50%. 10 over 20. Okay? There's 10 short jobs, each with 10 tickets, 1 long job with 1 ticket. Okay? How many tickets do we have in the system? 0, 1. Okay? A short job is going to win with probability 10 over 101. A long job is going to win with probability 1 over 101. Okay, this is approximately 10% is approximately 1%. And vice versa. Okay, so here we have 1 and 10, and you can do the math. Here you get 50%, and that one will get 5%. Because there are 10 long jobs, each get 5%, cumulatively they'll get 50%, and this one gets, this one small job gets the other 50%. Because you can control based on assigning these tickets, what happened and so on. Okay? Any questions on lottery scheduling? Yes.
So is the lottery scheduling affecting the time slice that they're getting, or just affecting the number of time slices?
Is it affecting the time slice that you're getting? I said nothing about the time slice in this case, right? So by default, the assumption in the schema, the lottery scheduling schema I have just presented here, you assume that every job gets the same time slice. Okay? Let's say 1 second or 100 milliseconds. Only thing you control by doing this is how frequently you actually win the lottery, thereby what fraction of the CPU time you get. We are not trying to have different time slices like we had in MLFQ, no. All jobs are in one queue, each has some number of lottery tickets, you run the lottery, you go and, this is like round robin had only one time slice, the same is true here. Okay. Any other questions? Okay. So very quick summary, we did first come first serve, we said it's not fair, poor average waiting time. We did round robin, it's fair, but average waiting time can be long. Okay. Shortest job first, okay, not necessarily fair. If you have starvation, you can't be fair, by definition. But average waiting time is optimal. Okay. Good scheme, can't implement it in practice. Multi-level feedback queue is approximation of SJF. Okay. It does everything SJF does, approximately, but you cannot, but it still has the starvation property. And we saw some ad hoc fixes to the starvation property. Right? And doesn't require any knowledge of the future. You're actually looking at past history to figure out what kind of a job it is and treat it accordingly. Okay? Lottery scheduler is a randomized scheduler. It's fair. You get CPU time that's proportional to the number of lottery tickets. It has no average waiting time, but not very predictable, so completely random. So at long periods of time, you will get the behavior you expect. If you look at any short window, you may see arbitrary things happening, because it's a randomized schedule after all. Okay? Right. So the thing to keep in mind is so far we have not modeled context switches or any of that in all the simple examples we have looked at. In practice, you have to think about context switches and how they impact the overhead in the system, choose time slices accordingly. Okay, so these are all practical matters you have to pay attention to when you design a real schedule. In this case, we just ignored all of that. Okay. So that I am actually going to switch to what, that is what we wanted to do yesterday. So today we are going to talk about threads. I presume that concurrency, for those of you who have taken 230, you have encountered threads before. You know what threads are, you have actually programmed with threads and so on. Okay. So I'm going to quickly introduce thread. Not everyone here has taken 230, so bear with me. I'm going to reintroduce the concept of a thread. And really the reason we want to look at threads here is not to learn what they are. That's assumed that you know based on 230, but rather how the kernel should deal with it. How should it implement this abstraction? How do you generalize whatever we saw for processes and scheduling and process control block, and how does it apply to threads and so on. So that's really the goal. Okay. So we'll talk about what are threads. We'll talk about what kind of threading packages exist. How do we schedule them? We'll just talk very briefly. Maybe not today, we run out of time. Okay. So let's talk about what is a thread and how is it different from a process. So let's assume that a process, we saw what a process was. It was a program in execution. We saw what the state of the process was. Anything that you need to, all the things you need to know to keep track of the process. Okay? So we'll assume a process defines the address space of that program that's executing the text segment, the resource segment, and so on. Okay? A thread within a process defines a single sequential execution stream. Okay, it's the execution stream within a process is referred to as a thread. Okay, so let me draw a picture of the process that we have seen so far. Segment. This is the picture I put up a few lectures. So this is what a process layout in memory looks like, and then we have the various pointers. So let's say this is that's the address space of the process. That's its layout in memory. Okay, this is the execution context of the process. This is the program counter is pointing to the instruction. That's the instruction you're executing next. Okay. This thing that is executing is essentially called the sequential execution stream of the process. That's really a thread within a process, a thread of execution inside that process. Okay. By definition, every process has one thread of execution sequence, one thread, and that's really the conventional view of what a process looks like. So when we talk about threads, we are really talking about multiple threads within the same process. We'll have multiple sequences of execution within that process. So here, the way to think about this, just make that bigger. The same address space, you could have two threads of execution. Okay? In this case, one thread of execution is executing that instruction. Another thread is also executing some code within the same process, and it's executing something in function foo. Okay? This is a process with two threads. You can generalize this to n threads. You can have n threads of execution. Each thread is executing a different code within that process, and it's independent of other threads. In this case, so this thread, whenever you schedule this thread, it's going to continue executing sequentially from this point on. Whenever you schedule that thread on the CPU, it's going to execute that part of the code and keep executing sequentially. And you may have more than that. You can have n threads here. Okay? So threads extract the thread of control information from the process. You can have multiple threads bound to the same process. As you can have a process with multiple threads. The thing to keep in mind is all of these threads share the same address space. Okay? They have the same code segment they are sharing. They will share the same heap. All the global variables will be shared. Okay? You don't need to have system calls to cooperate between threads. You will use the threads library, as we'll see. And you'll see that writing a process with multiple threads that cooperate is much simpler than writing multiple processes that cooperate. When we talked about cooperating processes, I talked about shared memory, I talked about message passing. You don't need to do any of that, as you will see. Okay, same picture shown slightly differently. Single threaded process. Okay, all the segments, there's one thread of execution here. Okay, this is also referred as a conventional process. In your single threaded process, you may as well call it a process. And that's what we know so far. It's a multi-threaded process. One address space, multiple things executing within that address space. Each of those things is called a thread of execution. Okay. So you will see the thing that you should keep in mind, each thread has its own stack, has its own registers, that are independent from other threads. Whenever this thread is scheduled for execution, it will work with that stack, and you have to load the appropriate stack pointers and so on, and it will have its own register values. Okay. If you switch from this thread to this thread, you have to save this state in the process control block and load that state. Just as when you switch from one process to another, you save the state of that process in the PCB and load the state of the new process. Same thing is true here. When you switch between threads, if they are threads of the same process, you will save this state and load that state. Okay, so that's the background, and here is some little more details of how you can view various operating systems. Okay, depending on how many address spaces are supported and how many threads are supported within an address space, you can have different scenarios you want an operating system support. This is a uniprocessor operating system. Okay? Single address space, single thread of control. Okay? Essentially mean you can have only one traditional process running at any given time, uniprogramming. Okay? All these others are scenarios of multi-programming but with different assumptions. Okay? Here is another scenario where your single address space, only one process can run at any given time, but you can have multiple threads within that process. So you can run one process, but it can be a multi-threaded process. Okay, in the uniprocessor case, you can only run a single-threaded program. Yes, you can run a multi-threaded program, but only one process, no more than one. Okay. These are generalizations. So you have old Unix, not today's Unix. This is not what Unix does at all. So you have, this is multi-programming, traditional multi-programming with process support only, no threading. Right? So you can have more than one process, each of these boxes is a process, and as is shown, with these things in there are threads. Okay? So you can have only one thread per process. So what that means is these old systems did not support multi-threading at all. You can have more than one process running, but there's only one thread within each process. It's a traditional process model. Okay? This is what we have today. You can have more than one processes. Each process can have one or more thread. It can be a traditional process or a multi-threaded program. Okay, so you'll see these are all address spaces or independent processes, and they are all. So practically any general purpose OS today will fall in this category. Okay. Special purpose OSs may still do this. These don't exist more or less unless you're doing embedded programming and you're writing directly onto the hardware. You will not see that at all. Okay. Any questions on this? These are just different kinds of scenarios you can expect to see in operating systems. This is just an example of the old producer-consumer problem that I mentioned earlier with threads built in. Okay. Still doesn't have synchronization. We'll get to that next time. But this is a multi-threaded variant of the producers and consumers. Okay. So you remember the producer and consumer. Right? So this producer produces some data item, it sticks it in the shared buffer, consumers consume from that shared buffer. Okay. That's the producer code, okay. Just an infinite loop producing data items. The consumer code also sits in the infinite loop consuming data items. Okay. Those conditions there ensure that there are no buffer overflows or under. Okay. The thing that is new is this. Okay. There's a main function, basically for two threads. You fork one thread and say you do the consumer code, you execute the consumer code, you fork another thread and you say you go execute the consumer code. So these two producers and consumer threads will run, in this case one producer and one consumer thread. Each of them will run concurrently, right? And they will execute the corresponding code, and this is the layout that you will see. So that's the code, which is this. You'll see that there are two program codes, one for thread 1, one for thread 2. The one for thread 1 will sit somewhere in between here. The one for thread 2 will be somewhere here. You just move and that one will be there. Those are the two. There are two stacks. one for thread 1 and one for thread 2. There's only one heap is always shared, and then you have some static variables. Okay? Every process, every thread will get its own stack, so that's represented here. It will get its own set of registers, including the program call that's shown here. Okay? Heap is always shared. Okay? Any questions on this?
Just a quick question on the thing that you have down there. It says or procedure called to a thread library. So if you are using a thread library, does that mean that the processor or the kernel isn't taking care of scheduling, that the thread library has to take care of that?
Good question. So you are asking a question that we'll get to in just one more. Okay, so it says you can create a thread either by calling a system call or by calling a procedure to the threads library. And the question is, if you make a new create a new thread by invoking a threads library rather than system call, is the threads library is responsible for scheduling, or is the kernel responsible for it? The answer to that question, it depends on whether you have a kernel level threads packet or a user level threads packet. We'll explain what those two things are, and then we'll see based on whether it's one or the other, who is responsible for the scheduling. Is it the kernel or the library or a bit of both? Okay. So that's really what we are going to get into. So depending on your OS, you may have to, so you can have various thread packages, but depending on the OS and how that package is implemented, you can have either kernel level threads package or a kernel level threads library or a user level threads package or user level library. Let's understand what those two mean. Okay. Was this also covered in 230? Those of you did 230? Yes, no? Forgotten. It's all done. Okay. We'll cover it anyway. I just want to know what is actually being done in 230 these days. So kernel level threads, as the name suggests, is threading support that the kernel provides out of the box. Okay? The kernel knows about the presence of threads within a process. Okay? So if the kernel knows, what that also means is to create a new thread within that process, you actually have to make a system call so that the kernel knows you're creating a new thread and it can account for it and so on and so forth. Okay? So it's essentially a thread that the OS knows about, and switching between kernel threads of the same process actually requires a small context switch at the kernel level. The kernel will actually save the state of that thread in the process control block. It will load the state of the new thread you are trying to run. Okay? So switching, context switching here actually involves the kernel. The overhead of switching between threads is actually going to be lower than overheads of switching between a process. You're only going to save the stack and the registers. But it's the same address space, so the memory management info, the page tables, all that don't change. So you don't need to save them. Only when you're switching between threads of different processes do you do the same you have the same overhead as switching between processes. But switching between threads of the same process, much more lightweight. Okay? Values of the register, PC, stack pointer must be changed. Memory management information does not need to be changed. Neither do you need to change all the file descriptors and all of that. Okay? But because the kernel knows about the threads, the kernel is also responsible for scheduling them. Okay? You're no longer going to say schedule process A. You actually have to say schedule thread 13 of process A. You have to pick a thread to run within that process. Okay, so the kernel is going to be responsible. Okay, but we can use the same processor scheduling algorithms we have looked at, MLFQ and so on. So that's the reason I was calling those things a job, because in this case, if you're multi-threading support, each of those is no longer a process, it's actually a thread that is the kernel knows about. So the jobs will actually be threads. You'll pick a thread for execution. Okay? And you'll see that, I already said, context switches between kernel threads is somewhat more lightweight. Okay, advantages and disadvantages we'll come to, but let's talk about user level. Okay? So user level threads packages are threads that your kernel doesn't know about. Okay? Entire support for threading is built at the user level in a library. The library is responsible for all aspects of thread management. Okay? So in this case, if you just say create a new thread, you just make a call to the library starts a new thread for you. From the application's perspective, is no different. I mean, you don't actually have to care whether this is being implemented in user levels or at the kernel, but from a systems designer's perspective, it matters quite a bit. Okay? So in this case, to create threads, to delete them, to do any synchronization, we just make library calls. And those library calls don't translate to system calls, these are just library calls. Right? So the OS, all that the OS knows about is here is a process. The fact that there are 3 threads within the process, the OS doesn't know, it cannot even see that information. Only the user level that the library can see. So in this case, scheduling actually is a 2-level decision. Okay? The CPU, the kernel is going to pick a process for execution. Okay? If within those process you have multiple user level threads, then there is going to be another scheduler that's implemented in the user level library, threads library, and then it has to run and pick which of the threads should I actually execute now that this process has been chosen for execution. Okay, 2 levels of decision making. The kernel picks, the kernel picks a process, the threads library picks a thread within that process. Yes.
Okay, so if you have like, if you're doing this like through the library instead of like through the kernel, and you're doing multi-core programming, what was I gonna say? So like if, like can you have the library schedule actually use multiple cores, or would you have to go through the kernel?
The question is a good question. It is something I would have gotten to in a moment, but let's address it now. Question is, if you have a multi-core system, okay, and a process gets chosen for execution, is the threads library then going to take 3 of its threads and run it on 3 cores? That's really the question. So, as we will see in a moment, the downside of user level threads is that the kernel doesn't know of their existence. The kernel doesn't even know that there are threads. It just looks at it only knows about processes. Okay? So if you have multiple cores, it doesn't know that this process has 3 threads, so maybe I should keep these 2 cores empty so the threads library can do something. It only knows a 1 thread, assume there's 1 thread of execution. So it's going to schedule that process. Okay? So the user level threads manager can only schedule 1 thread on that core that you have been chosen to run. There is no real concurrency in user level threads. You cannot actually use multiple cores. Because from the OS's perspective, this is a traditional process. Okay, the fact that there are threads within the process is not known to it. It treats them as user level process. So you cannot actually get benefit of concurrency by running on multiple cores in the user level threads library. Yes.
Is this anything like green threads?
Is this anything like?
Green threads?
Okay, explain what green threads are.
I don't know. This is my understanding of green threads. I was wondering if that's a different name for it.
No, so I don't know what green threads are. This seem to indicate something else. I can look it up. But user level threads, there are many packages on user level threads. User level threads are actually things that are implemented in user space, right? So that's really what it is. There are many, so I will talk about Java threads and POSIX threads. So you can take any of these APIs and you can decide whether to implement them as kernel level or user level. So you, the threads designer, can decide what you want. You want to implement this completely in user space, do you want to use kernel support? Okay? So you can use the same API, you can write P threads or even Java threads with or without kernel support. Early versions of JVM were written as user level threads package. You could still do Java threads and get all the great features of concurrency, except that you cannot use multiple cores, but all the rest is the same. Okay? So this is a picture that seems to indicate so these are processes that the kernel knows about. In this case, this process and this process is traditional single thread. Okay, here you will see multiple user threads, but from a kernel's perspective, it doesn't know. Okay? Its PCB will assume this is a single threaded process. Okay? Something else is actually going to deal with all the threads. We don't have to worry about it at the kernel level. Okay? So let's talk about advantages and disadvantages. Okay? Advantages of user level threads. First advantage is you don't need kernel support to implement threads. You can even take an OS that has absolutely no kernel support for threads and yet implement a user level threads library and run multi-threaded code. Okay, you're not depending on the kernel. In fact, this is how early threads libraries were implemented. You could actually implement a threads package in DOS. Okay? Uniprogramming supports only 1 threads at the kernel level. If you want to write multi-threaded code in this case, the only way you are going to do that is you will implement a user level threads package. Because the kernel just schedules and then the user level threads package introduces the threads abstraction to the process. So even without any kernel support, you can actually write multi-threaded code. Good thing. Okay? Number 2, okay, user level threads are a lot more efficient than kernel level threads in terms of overheads. Okay? Because creating threads, deleting thread, all the synchronization calls are very lightweight function calls to a library. They're not system calls. Okay? You call create thread, it just goes to the library. That's a function call within that same process. Okay? If you call create thread and it's a system call, that's a much more overhead. So thread management is much more efficient in a user level thread. Okay? Advantage 3 is that thread scheduling is also more flexible. You are not bound by what the kernel's CPU scheduler is. Okay? If your process gets chosen for execution, you can implement whatever thread scheduler you want in that process. So it's underneath it may be round robin or MLFQ. Here you can say I'm going to do lottery scheduling in my threads. And you can do that. Okay, whenever your process gets to run, you run a lottery among your threads and you do whatever the lottery scheduler. Okay. So you are no longer bound if you want to do scheduling within that process by whatever the kernel is doing for you. You can pick other schedules. Okay. Those are all advantages. Okay. And there are two main disadvantages, which I think are on the next slide. Okay. First disadvantage is basically the advantage also works against you. Since the kernel doesn't know about the existence of threads, it doesn't know how to schedule you in any way any better than it schedules a single threaded process, a traditional process. Okay. What does that mean? If process A has 10 threads and process B has 1 thread, they may still get the same amount of CPU time. Okay. If you had kernel level threads, process A would have 10 schedulable entities in the kernel. Process B would have 1. So if you have a fair scheduler, process A might get 10 times the CPU time as process B, because you schedule all, if you're doing a round robin, you schedule 10 of those threads and then 1 thread of the other process. Okay? So you don't know about the threads, so you cannot make any informed decision. You will just treat it as there are no threads in there. Okay? That's one problem. Second problem is that if any of your threads start doing I/O, your entire process is going to block. Okay, you may have 100 threads, one of them makes an I/O call. Okay? So since you don't know that there are threads in your CPU's kernel is going to take that entire process and put it on the main. Okay? All the other threads may be actually ready to run. Kernel doesn't know about them. Okay? So if one thread blocks, all of them block. Okay? In kernel level threads, that's not true. If that thread does I/O, only that thread goes to the wait queue. The other threads still stay in the ready queue and they will actually run. So your process can continue to make progress even if some threads are blocked and others are not. That's not true in user level threads. Okay? The last disadvantage is what we just talked about. If your user level threads, you are not going to be truly parallel if you have multi-core system. Okay? Because you can only, kernel can only schedule that process, it doesn't know anything about threads inside it. If you have kernel level threads, you will get true parallelism. Okay? 2 threads of the same process, same address space can actually run in parallel on 2 cores, and you will actually get twice that CPU time than if you have process level parallelism. Any questions? Okay. So I'm going to talk about Solaris, a Unix operating system which was designed by Sun, now owned by Oracle. It's one of the few Unix systems that are still in existence. Okay, it actually, so a lot of these innovations actually came from Solaris. Solaris implemented the first threading package, okay, which eventually became Solaris threads, which eventually became pthread. Okay. You'll also see that they also implemented the first remote procedure call in the commercial operating system when we do distributed system. They also came up with NFS, the network file system. So a lot of these OS innovations, although they are not the inventors of those mechanisms, they are the first ones to put them into a commercial, widely available operating system back in those days. So here is how Solaris works. So Solaris actually introduced the notion of kernel level, but it is a lot more flexible than the model I just talked about. Okay, Solaris actually uses the notion of a lightweight process. Okay? So the way to see it is that box is an address space. These sort of curly arrows in the box are user level threads. Okay? The circles within the box are lightweight processes. Lightweight processes are entities within a process that the kernel actually knows about and can schedule independently of others. Okay? And then it also has kernel level threads that lightweight processes are mapped into. Okay, so more complex scheme, let me explain why you need all this sophistication. Okay, so what this allows you to do is have a lot more flexibility on how threads are getting scheduled. Okay, you can decide if you have some group of threads, how they're mapped onto however the scheduler is going to schedule them. So in this case, just to give a very simple example, let's just take this process. It has 3 threads. Okay, those are the 3 threads. It has 2 lightweight processes, and these 2 threads are mapped to this lightweight process. This thread is mapped to that lightweight process. As far as the kernel goes, it is going to decide whether to schedule this lightweight process or this lightweight process. If it schedules this lightweight process, then that thread will automatically run because there's only one thread mapped onto it. Okay? If it runs this lightweight process, there's another scheduler. This is like the user level thread scheduler is going to run and say, this lightweight process has been scheduled. There are 2 user level threads mapped onto it. Which one should I run? Okay? And then you can pick which of those 2 should run. Okay? So you can control how many lightweight processes you want in the system, how many user threads you have, and how to map them. So you can have, so by default you just have a one-to-one mapping. For every user level threads process, there's one lightweight process. So whenever this one is picked, that one will run. But you can have this more sophisticated scheme, many to many, many to one mapping and so on. Okay, so this is best shown in a, so rather than this picture, I think this is a slightly better picture to show the same thing. Okay. So this is a user level threads package. This picture, it's a many to one mapping. As far as the kernel is concerned, it knows that there's only one thing it can schedule, that's the process itself. And then many user threads mapped onto that process. So whenever you schedule this, you are going to pick one of those threads and schedule it. And which one you pick depends on the user level scheduler. This is a traditional kernel level threads package. For every thread that is represented in user space, there is an entity that the kernel knows about and will schedule. Okay, that's a kernel level thread. So whenever, and these 2 might belong to process A, those 2 might belong to process B. The process mapping is not shown. Okay? So this, whenever you pick this, that one. Whenever you pick this kernel thread, that's when you get to execute it. So these 2 are more sophisticated mappings. And here you have a many to many mapping. Okay? These are actually bound to any of this. So whenever this runs, you can pick any of those 2. Whenever this runs, the same is true. Here you have one kernel level thread that has a one-to-one mapping, one has many to one. And you can decide these mappings when you create your threads. If you use POSIX threads to write your code, which is a C and C++ package, you can pass arguments if you have a kernel level thread saying, whenever you create a new thread, should there be a new kernel level threads created, or should I map this user level thread to an existing lightweight process? So you can specify all of this. Okay, so you have fairly complex ways by which you can control how threads within your applications are mapped into whatever the kernel can see and schedule. All of this sophistication only to have more flexibility in CPU scheduling. Other than that, it doesn't buy you anything. Okay? So if you want to have very careful control over your scheduling, you can actually do these kinds of things. Okay? All right. So very quickly, I'll talk about threads libraries and then we are going to stop. Okay, so we talked about threads, we talked about user level, kernel level threads, their pros and cons. I mentioned how threads get mapped onto kernel level threads, the flexible mappings. Okay, so I'll not talk about these libraries. So there are really 2 main libraries, actually 3, but you can think of them as 2 that typically are used. Okay, so if you are in the Java world, you use Java threads. JVM support. Okay, Java supports threads out of the box as part of the language runtime, so you end up using Java threads. If you are in C or C++ world, you will use POSIX threads. POSIX is a standard. They define the API. So any OS that supports POSIX threads, you can write your code against and it will just run out of the box. If you write your code using POSIX thread, you can run it on any system that also supports POSIX threads. The same API. Just as if you write your code, Java code using Java threads, so long as there is a JVM, it will run. Whether it's on Unix or Windows, doesn't matter. Code is portable, same kind of stuff. Your code you can recompile and it should run. Okay. Now, how you implement these Java threads or POSIX thread is left to the designer. You only specify, both of them specify an API, saying the programs will call this API. Should you use user level threads, kernel level threads, That's up to the JVM designer or the pthreads designer. Okay? So pthreads is basically, as I said, POSIX standard. It's common in most Unix-like operating systems. Today Windows also supports pthreads, but Windows has its own implementation of threads called Windows threads, okay, which are similar but not the same. Okay, Windows supports both, but these are native Windows threads, and POSIX threads are written as a layer, a wrapper on top of Win32 threads. Okay. Java threads, I presume, is what you used in 230, okay, implemented by the JVM. Okay, and I'll show you some couple of examples so you can do thread manage. Okay, so here are some small snippets of code that show POSIX thread creation, Windows thread creation, Java thread creation. Okay, so you are basically going to use pthread create to create a new thread. Okay. In C or C++, in Win32, you are going to call the create thread equivalent call, different API. In Java thread, you'll just say new thread and call T++. They will all basically allow you to create a thread. Okay. Different languages, different APIs. Okay. And you may have multiple implementations of each of them, user level, kernel level, and that's also different. Okay. Now, as far as this class is concerned, anytime you do threads, you will be here. Okay. Most of our assignment, except for the first assignment, are actually Java. Okay. So, with that, I have just a few minutes. I'm going to talk quickly about the lab. There will be a lot more details on the lab in the next discussion. Okay. So first lab is already up there, due in 2 weeks. Okay. We recommend, this is a fairly simple lab, warm-up. So this is supposed to be done as an individual project because it's very straightforward. Starting lab 2, you will actually have to form groups and do the assignment because the complexity of the lab will keep growing. Okay, this one we are going to start off as simple, so you don't have to do this as a group assignment, you do this individually. Lab 2 onwards, highly recommended that you do group. We are not going to force you to be a group in lab 2, but you should try to be a group. In lab 1, you should not do this individually. Okay, it's a very simple assignment on system calls. Okay, so what you have to do really, this assignment has 2 parts. Okay. First requires you to write some code to use system calls. The second just shows you how system calls are actually implemented in a kernel. Okay. One makes you use a system call, the other one shows you how to implement a system call. Okay. Although that might sound a bit scary, it's not as bad as it seems, with some caveats. Okay. So how to use a system call, that part of the assignment is actually going to be done in C, okay, not in Java. If you don't know C, don't worry about it because there are barely 10 or 15 lines of code you have to write. Okay? None of them involve pointers or anything like that, so it really looks like Java code for all practical purposes. There's enough hand-holding here that you should really not even take more than a day to finish that part of the assignment. Okay? And what you really have to do, the system calls you have to use are fork and wait and exec. Okay? Same stuff I did in the class. Okay? So we basically we will tell you, saying you start this program, 3 children, child processes, have each of the child do the following, and then kill them or wait for them or whatever, and you will have to write some code that is essentially going to do fork and exec. Okay? And we'll see that it's basically, I won't go into the too many details, but that's really what it is. There is already some code there. Okay, so that is a C program that does not have fork actually as an exec, so you just have to go in there and put the fork in the right places and then put the assignment. It is pretty much done at that point. Okay? Fairly straightforward to do. Okay. Second part is actually in Java. Here there's a different quirk, which is that you have to actually do this in this toy OS called Nachos. Okay. This is actually, the assignment is specified to a detail where I think you don't really have to think. There are very detailed steps. You just go and do those steps and you will see what needs to be done to implement the system. The reason I put this assignment is really, this part is not really an assignment, it's just a set of directions that you are just going to go and execute, and you will have a system call implemented at the end of the day. That system call is just going to print hello and nothing else. So that the important part is the steps you have to do. Those steps actually, interestingly enough, turn out to be the same things you have to do to implement a system call in Linux. Okay? So you have to define a new system call, give it a unique number, define a handler for the system call. So whenever a trap occurs, you call the handler, and in the handler you write the code for the system call. Here the code is just going to print hello world. Okay? But the structure of what you do is what is more important, not the system call itself. And that mirrors what you do in a real version, which is why I thought it's interesting to do this. Okay? This will also be a very gentle introduction to Nachos, okay? Which is a toy operating system. It's something I think you should get familiar with now. With this assignment, it's very straightforward. The next one will have a little more detail of what you need to do. Okay? So assignment in two parts. Use fork exec system calls, C code, but there is enough template code provided that you don't have to worry too much about what needs to be written. Just get a structure of fork and exec and all the if statements right, and the core assignment is pretty much done at that point. Second part is going to walk you through how to implement a system. Okay? And next Wednesday you will have a lot more discussion. Just go through this and get started if you want, and come back with questions.
So we're going to end up using a lot more of the Nachos operating system, or?